Hello everybody, how are you doing? Today we'll work on normal distribution, on the normal distribution. Normal distribution. Normal distribution. For example, x is a random variable. And each experiment, each outcome of experiment doesn't it's better to say is respective to the previous one. We can say that x has a normal distribution if its probability density function can be written down using this formula. P or x equal 1 over sigma square root of double P times e raised to power x minus mu squared to sigma squared. This formula refers to the so-called normal distribution. Some people say normal distribution is a Gauss distribution. Gauss or Gauss distribution or Gaussian distribution or Gaussian distribution. Here sigma is a standard deviation and mu is a mean or math expectancy. Some people say normal distribution like a Bell distribution because its graph has a bell form. It has no lopsided, no skew, and it's not lopsided right and with a long tail or something else. It is very symmetrical bell-shaped distribution, and it seems to be like this. It has usually this graph here x and here probability thing. Here the middle part is very middle, it is x, it is mu point, the mean of the distribution. We have two saddle points here and here, and they have x is mu plus sigma, mu minus sigma here. What else can we say? I put here p equal 1 over sigma square root of 2 pi e raised to power 1 over 2 x minus mu squared over sigma squared. Why it's so important thing? Normal distribution works as a kind of a reference distribution. An example. You can say that as much a real distribution is different from normal distribution. As many special factors influence or impact the random experiment. Example. For example, you have p equal 1 over 2, for example, 2 pi exponent 1 over 2 x minus 3 over 4 squared. For example, you can see, and you have to know what is mu here and standard deviation, the standard deviation. So you can compare this formula in the general view of the normal distribution. You can notice that mu equal 3 here, the mean value of the mean of this distribution, and standard deviation is 2. So variance over this distribution sigma squared is 2 squared, and it is 4. Very often you can face with the z distribution, z normal distribution, and it is distribution then mu equal 0 and sigma equal 1. So you can turn your formula into this one. E equal 1 over square root of 2 pi e raised to power 1 over 2 x squared, because mu equal 0 and sigma equal 1. This is the z distribution, and sometimes it is very convenient to use it to calculate different situations. Some researchers approximate distribution of any random variable which distribution is unknown. Why does it work? It infers from central limit theorem. Central limit theorem. The central limit theorem states that sum of n number of random variable x converges to normal distribution if n tends to infinity. If n tends to very large amount. So if you made a very large number of experiments and consider the summation of these random variables which you get through your experiments, their sum has distribution very close to the normal distribution. Since that this distribution is getting very important in statistics, and even it is considering as a reference distribution. Okay. Also, one very important property of the normal distribution is the coverage of the data fetched during some experiments. I put here this scheme. If it is axis x, it is axis y. Here we have mu and very symmetrical bell-shaped view of the normal distribution. Cut, and you cut here. So here you have mu plus sigma, mu minus sigma. Here mu plus double sigma, mu minus double sigma, and here you have mu plus 3 sigma and mu minus 3 sigma. We can say that into this green shaded area this green shaded area covers the about 68% of all outcomes during your experiments. For example, if you try to measure height of students in Ижевsk State University, 68% of all students, with regard to their height, they get into this green area. Okay, into this red shaded area, this red shaded area covers about 45–90% of all outcomes during your experiment, and 6 sigma area covers about 99.8% of all experiments. And these ideas drives us at an idea an idea of confidence intervals. Confidence intervals. What does it mean? I want to explain just to make it clear on your hand, viscerally clear. For example, you made n number of experiments. N is large enough number. If you calculate mean value and standard deviation, and you can define the interval mu minus sigma, mu plus sigma, this interval includes the real mean value, real mean or grand mean, real mean, with confidence 99.8%, with the confidence 99.8%. So it means that your result of your experiment have range of credence or rate of credence about 99.8% within interval mu minus sigma, mu plus sigma. Okay. I think it's enough for your theoretical part, and now we have two examples. How we can use this normal distribution. Example. For example, you consider a hospital, and here some people treated. Here people treated survive with probability equal and they pass away. This probability consequently 1, I denote like Q, 0.999. And I want to define, so this is very classical binomial distribution. Because we have just two outcomes. So people, they can survive or pass away, or maybe little outcome here. And for example, I want to know what is the probability that among 10,000 patients, 900 and 9,900 will survive, or maybe 100 they pass away. I can use the the formula for probability, binomial probability, P equal C n chooses R times P raised to power n times R times Q raised to power n minus R. And if I put all of these numbers into this formula, I have this formula C and choose R can be expanded n factorial over n minus r factorial times r factorial p raised to power of r q raised to power of n minus r. And we have n equal 1000 n minus r 100 factorial, and here we have 90 factorial. P, it is O point raised to power r, it is and the other one formula Q, it is 0.001 raised to power 100. If you try to calculate this result and input this factorial 10,000 factorial, you will have an error. But we can approximate this formula using the normal distribution. I can put it here. Normal distribution. Sigma square root of 2 pi times e raised to power 1 over 2 x minus mu squared over sigma squared. Okay. We have to put here sigma and mu. Maybe you remember that for binomial distribution, if you don't mind, I want to clean here. You have mu equal np for binomial distribution, and sigma equals square root of p times and sigma equal square root of np times 1 minus p. Now we are ready to put into this formula. Since that probability that among 10,000 patients 9,900 will survive, they have 1 over square root of 2 pi np 1 minus np and exponential thing 1 over 2 x minus mu it is np square root of np 1 minus p. So I'm ready. It is squared and squared, and now I can put here as numbers. So this probability is 1 over 2 pi square root n equal 10,000 times 0.999 times 0.1 exponent 1 over 2 x minus 10,000 and 5 squared over square root of 10,000. P was 0.999 times 1 minus 0.1, and all this thing is squared. So this formula gives you approximately result probability that among 10,000 patients, 9,900 will survive. A probability that they survive is 0.19. One of them survived, 0.999. Approximation, but it works pretty good.